Okay, well, thank you. Can you all hear me? More or less well. Just adjusting this. So I'm telling you about about neutrinos and cosmology. And normally you wouldn't think about these two things together because after all, neutrinos are one of the lightest and most weakly interacting particles that we know about. Whereas cosmology, on the other hand, is the study of the universe. So in other words, it is a subject that concerns gravitation on the largest observable scales. And yet, if you put these two things together, there's a very interesting prediction that comes about, and that is the cosmic neutrino background. Okay? And it's a thermal background that was produced 1 second after the Big Bang, when the temperature of the universe was about 1 MeV. So that's basically what I'm going to be telling you about today, all about the cosmic neutrino background. And here's roughly how I will go about doing, telling you about all the fun things that we can do with this cosmic neutrino background. First, I'll tell you a little bit about the background about the neutrinos and cosmology. I'll introduce the cosmic neutrino background in a bit more detail, and then I'll tell you about the observational evidence that we have at the moment for this C nu b. And then in the second half, I'll tell you about neutrino hot dark matter, in particular how we can use cosmological observations to constrain neutrino masses. And last but not least, if I still have time, I will tell you about other non-standard properties of neutrinos that we can potentially also constrain using cosmological observations. Okay, so here we go. So first of all, here's the standard model of particle physics, which I guess most people will know about. It's the most self-consistent and verified fundamental theory of nature yet. The 3 generations of matter particles, and it describes 3 of the 4 fundamental forces, so electromagnetism, weak interaction, and strong interaction. And neutrinos occupy this space down here. They're fermions, and there's 3 generations, so there's 3 flavors, 3 types of neutrinos, in other words. And they are very light. We believe they have masses that at the moment, all the observational evidence, experimental evidence, point to them being having sub-electron volt masses. Okay, so just to compare with the electron mass is about 500 keV. So these neutrinos are like millions of times, possibly 1,000 millions of times lighter than the electron. They are electrically neutral particles, so they have no electric charge. And in fact, the only force they ever feel is the weak force. Okay. Now, this standard model is, of course, not a complete theory because there are tons of things it doesn't explain. There are also theoretical issues with it, but that's not my department. This theory is not complete as said. It doesn't contain a dark matter particle. Okay, dark matter being one of the main unsolved puzzles today. It doesn't incorporate gravity. It doesn't explain why we have more matter today than we have antimatter. It doesn't explain neutrino masses, etc. But even if we just take the stuff that the standard model does explain, so that essentially all the phenomena, most of the phenomena that we see below energies of about a TeV, there are interesting things that the standard model does predict if you put it in a cosmological context. Okay, so at this point, I'm going to switch to cosmology. Okay, so the current model of cosmology that we have at the moment is the standard hot Big Bang. And essentially, the central feature of this model is that you start off with a very hot universe, where all the energy densities are concentrated in a point, and then you have this expansion of space. Okay, so in the first, say, up to about 100,000 years after the Big Bang, the universe was an extremely hot and dense place. Okay, what this means is that if you go back in time to this first 100,000 years in the universe, there will be particle physics processes that you wouldn't normally see in the everyday, under everyday conditions. So I call this the particle physics era. Now, most of these particle interactions are transients in the sense that you might make some very heavy particle, but then they decay, so they leave no signatures. But there are also processes that have left behind what is called relics. Okay? Things that are just surviving there, they don't disappear, and they've survived to the present time for us to observe. And for the standard model, once you embed the standard model in this expanding space picture, there are 3 types of relics that are the standard predictions, essentially. So we have the cosmic microwave background, which was created 400,000 years after the Big Bang. We have the cosmic neutrino background, which is the topic of this talk, and also some light elements that are predicted, like deuterium, helium-4, all the way up to trace amounts of carbon that should have been produced in the first 20 minutes after the Big Bang. Now, let me just say a couple of words about the CMB, because it's probably by far the most famous relic that we know about. So, the CMB is a thermal photon background that was formed at a time about 400,000 years after the Big Bang, when the universe had a temperature of about 0.2 electron volt. So converting that into Kelvin, that's about 3,000 Kelvin. So it's just a little bit cooler than the surface of the sun. And these photons are the first photons that we can see, and the reason is that if you go to temperatures above 3,000 Kelvin, then what you have is a hot soup of free electrons and protons, and any photon that would be living in this soup of electrons and free electrons and protons will be doing a random walk, because every time they encounter an electron, they will bounce off, and another one will bounce off, and every time they bounce off, they change directions. So the photons are doing a random walk in this soup of free electrons and protons. And in fact, they are scattering off these free electrons at such a large rate that you actually have equilibrium being achieved in this setting. Okay? But then the universe expands, as we know, and with expansion comes cooling. So you wait a little bit of time, the temperature will drop down to below 3,000 Kelvin. And what's interesting here when the universe cools to a temperature below 3,000 Kelvin is that energetically the electrons and the protons would prefer to come together to be in a bound state. Okay? So what you have is that on the left, at high temperatures, you have a plasma, an ionized plasma or free charged particles, but then you cool it down, and then what you have are these neutral atoms. And what it means for the photons is that now you no longer have these free charged particles for the photons to scatter on. And so at these lower temperatures, the photons can free stream. Okay? They can free stream to infinity. And by the time these photons free stream, after about 13.8 billion years, they free stream for us to observe, and we observe these photons as the cosmic microwave background. And the photons appear to come from a surface at a time when the universe had a temperature of 0.2 electron volt, and that surface is called the last scattering surface. It's as said, as the oldest light. The production mechanism of these photons is essentially thermal processes. So we expect the photons to take on a black body spectrum. Okay. At the time of production, it had a temperature of about 3,000 Kelvin. But because of the expansion of the universe, they would have cooled today to about 3 Kelvin. Okay, so this is the so-called 3-degree background, which was first predicted by Alpha and Herman back in 1948. Okay. And today, of course, we have seen the CMB. We've seen the CMB. The discovery of the CMB was actually completely by chance. It was back in '65 by Penzias Wilson. They were just playing around with their radio telescope, and then they found the CMB quite accidentally. They just saw this noisy background. They had no idea what it was, and they had talked to the cosmologists and realized that they had actually detected something really important. And they got a Nobel Prize for that discovery. And today we have several more generations of CMB observations. So in the 1990s, we had COBE. COBE actually had two functions. It was there to measure the black body spectrum, and they did a fantastic job. These days, the CMB is the most perfect black body we've ever measured anywhere in nature. The second function of COBE was to detect these tiny fluctuations, spatial fluctuations in the CMB. Okay, so these fluctuations were actually predicted by Peebles already back in the 70s, and COBE saw them for the first time in their measurements. They are like 10 to the minus 5 in amplitude of fluctuations, and in the noughties, WMAP confirmed this again. And the most recent measurement was from the ESA Planck mission, okay, which had achieved a much better resolution. So several Nobel Prizes. I don't know what happened to this one, but it's supposed to be a Nobel medal over there. Okay, so that's the cosmic neutrino background. What about the microwave background? What about the cosmic neutrino background? Well, as you can see here, cosmic microwave background is over here, and the cosmic neutrino background was predicted at an earlier time when the universe was about 1 second old. But the physics behind the production of this formation of this neutrino background is actually quite similar to the formation of the CMB. And again, we're talking about scattering, okay? And here we are looking at a much higher temperature, and a temperature of about 1 MeV, so corresponding to 10 billion Kelvin. And what's interesting here, these extremely high temperatures, is that even the weak interactions are occurring sufficiently frequently to allow neutrinos to scatter off things. Okay, so you imagine again you have a bath, and this time your bath is full of electrons and positrons, and maybe a trace amount of nucleons, but mostly electrons and positrons. And what the neutrinos are doing again is that they see an electron, they'll bounce off. Positron as well, they'll bounce off positrons and then change directions. And in fact, the neutrinos can even bounce off each other. Okay, this is how dense things were back at a time when the universe's temperature was 1 MeV. And again, because of this frequent scattering, we are able to thermalize these neutrinos. So they come with a thermal distribution. And again, as the universe cools and expands and cools, at some point, these weak interactions are not able to catch up, to keep up with the expansion rate. And so once you drop to a temperature of below 1 MeV, the neutrinos don't manage to find electrons or positrons or other electrons to scatter off. And then from that point onward, they will free stream to infinity. And whatever we can see of these neutrinos, that would be the cosmic neutrino background. Okay. Now, it's just some vital statistics of the C nu B. So it's a thermal background, like the photons. But unlike the photons, because the neutrinos are fermions, the distribution will be a Fermi-Dirac distribution as opposed to a Planck spectrum. There's a very nice relation between the temperature of the neutrino background and the CMB background. It's basically they are proportional to each other, and then this prefactor over here is essentially something that is fixed by standard model physics. Okay, and since we know the photon background is about 3 degrees or 2.73 degrees if you want to Kelvin, if you want to be a bit more precise, then we also have a prediction for this C nu B temperature of 1.95 Kelvin. Now, knowing the temperature of these neutrinos and knowing that they follow a Fermi-Dirac distribution is very easy to compute how many neutrinos we should expect. And when you do that calculation, what you'll find is that we have about 100 neutrinos plus antineutrinos per family in 1 cubic centimeter. Okay, so if we have 3 families, we'll be talking about 300 neutrinos in this much space on average. Okay? The energy density ratio is also something you can establish. And it's actually just this ratio 0.68. So energy density in neutrinos versus the energy density in photons. So if you just take these numbers and then contrast these numbers with all the other natural sources of neutrinos that we know, we come up with this grand unified neutrino spectrum. It's actually a picture I took out of this paper. And what you see here are all the sources of neutrinos we've seen: atmospheric, solar, reactor neutrinos, etc. And the C nu B neutrinos are by far the most abundant neutrino source in nature. Okay? In fact, there's so many neutrinos that the only particle that beats it are the CMB photons, okay, in terms of the number density. Okay, so we have a lot of C nu B around. Can we detect them? Well, a lot of people have thought about this for a very long time. And the best idea is still this one. And it's due to Steven Weinberg, and he already came up with that idea back in 1962. But there's been a bit of revival in the interest to detect this background. And the idea here is that you use a beta decaying nucleus to try to capture a background neutrino. So this schematic here, what I show here, are basically the energy of the electron for 2 processes. So the yellow line here corresponds to the process of nucleon decay, so n going to n prime, you have an electron and an antineutrino. And the yellow line here shows the spectrum, the end point of the spectrum of the electron, and energy of the electron. But if you have the first process, then the second process is also allowed. Okay, the second process, what do you have? We have basically a decaying nucleus, and it captures one of the 300 per cubic centimeter neutrinos that are floating around. Okay, and that turns into another nucleus plus an electron. And the signal for the second process is this monochromatic peak. Okay? It's monochromatic because the energy density of the neutrinos are expected to be dominated by the rest mass energy today. And there's not much of a spread, because so it's more or less monochromatic, but in reality there will be a little bit of a spread. And the key point here is that if you look at the gap between the endpoint spectrum of the first process and this monochromatic scale, this monochromatic signal, the gap between them is 2 times the neutrino mass. So what this tells you is that the detection of the relic neutrino, the C nu B relic neutrino background, is very intimately tied with the whole neutrino mass measurement game. Okay? Now, you can try to estimate how many events you can get, okay, for this monochromatic signal. And some people have done that, and they consider tritium beta decay, and they ask, if I have 100 grams of tritium, how many events will I expect for this peak? And what they found is about maybe 10, okay, not a lot. Now, it requires 100 grams of tritium. This is the most advanced tritium beta decay experiment we have at the moment. It's the Karlsruhe tritium neutrino experiment in Karlsruhe, Germany. This is their spectrometer. There's a funny story behind how they transported this spectrometer. And it's basically they're looking at tritium beta decay and measuring the electron that comes out of it, and precisely, this endpoint spectrum that I was talking about. They have 0.1 milligrams of tritium. So comparing this, the amount of tritium that is in this experiment and the amount of tritium that you need to even get 10 events, it's well, huge difference. And in fact, I asked someone if there's even 100 grams of tritium on Earth, because it's not something that occurs naturally. You have to make them somehow in a lab. I was told that there is, but it's not like we have kilograms or tons of these things. It's not a lot of tritium around. Anyway, so the bottom line is that it doesn't look like it's very feasible. Well, certainly not so feasible with Katrin. But there's one more parameter we can play with, and that is, as you can see, the local neutrino overdensity. Because when these people estimated this rate, they just assumed a homogeneous and isotropic distribution of neutrinos. But in reality, that is not completely true, and that is because we live in the galaxy, we live in the Milky Way, and the Milky Way itself is surrounded by a halo, and this is basically a gravitational source. So if you have neutrinos that are flying around, we would expect some of these neutrinos to come and cluster a little bit. But even if you allow for the possibility of clustering, it turns out that this is not such an easy, you do need a pretty large local overdensity to generate a signal for Katrin. So these people actually estimated that in 2010, and this analysis was also taken up by the Katrin experiment back in 2022. And what they found is that if you want to generate a signal, Rayleigh neutrino background signal in Katrin, what you need is a 10 to the 9 local overdensity of neutrinos. 10 to the 9. Okay, that's 1 billion. Okay, not just a factor of 10. And this plot is a bit hard to read, but essentially what this here shows you the overdensity, and you need to be up here in order to get a signal for Katrin. Whereas if you consider realistic modeling of how much clustering we should expect of these neutrinos in the Milky Way, the prediction is maybe 10 at most. Okay? So bottom line is that trying to detect the C nu B in the lab is probably not going to happen anytime soon. Okay? But there are other ways in which we can try to indirectly establish the presence of the C nu B. And that comes about if we look for imprints of the C nu B on cosmological observables. Okay? So that we go to this part. Okay, looking for C nu B in the cosmological observables. So again, this is an old topic, and people have already started thinking about this a long time ago. And essentially the idea of looking for the C nu B in cosmological observables rests on the fact that if you have this neutrino background, then this neutrino background will have an energy density. And this energy density will affect the rate at which the universe expands. Okay, so this expression here is the expression for the Hubble expansion rate, h. And on the right-hand side, that's the dependence of the expansion rate on things like the amount of non-relativistic matter, so omega m, the amount of radiation that we have, the amount of, well, cosmological constant, or dark energy, if you like, and spatial curvature, and whatever other stuff that you may have, you can keep adding to this expression to account for the energy density. Now, if we are interested to test the effect of the neutrino background on things like the CMB or maybe the light elements, then we'll be looking at fairly early times. And at fairly early times, the neutrinos behave like a kind of radiation. So they will contribute to this term over here. So omega r is reduced energy density in radiation, and we expect the neutrinos to contribute over here. And so expanding this out, that's the energy density in radiation that we expect in the standard lambda CDM model. Mainly due to photons, and we also have the energy density from the C nu B. Now, it's common for us to reparameterize this energy density in the C nu B in terms of this parameter called N effective. So essentially what you do is that, well, okay, you re-express this rho C nu B as a fraction of the energy density in the CMB, and then you factor out this part over here, this stuff over here, which is basically the energy density in one family of neutrinos with exactly the temperature that I showed you earlier. And then whatever corrections, you'll just lump here into this N effective parameter. Okay? So this N effective parameter, in other words, is not an integer, okay? But it's just an energy density ratio. And you can calculate this energy density ratio very precisely. And the number, the most precise number at the moment is like 3.0440, and there are even error bars around it. So it's 3 because we have 3 families of neutrinos, but because of the fact that N effective is actually an energy density ratio and not an integer, there are corrections, there are percent level corrections coming from things like finite temperature effects, neutrino oscillations, non-instantaneous decoupling, so on and so forth. Okay? This is something that you can do very precisely if you want to. And some people like doing these things, including me. Okay. Now, as said, trying to detect this C nu B background or trying to detect N effective, it's actually a really old subject. And I think this was the first paper that came out in 1977 on this subject by some of the founding fathers of the subject of astroparticle physics, particle cosmology. And essentially what they were doing is that they were looking at the helium-4 abundance. So as I mentioned earlier, helium-4 is also one of the relics that we can see. Okay? And the idea here is that if you make these light elements in the early universe and you're making them in an expanding universe, then how fast the universe expands will affect how much yield you have for these elements. And what is particularly cool is that this process of the formation of these light elements occurs just after the C nu B is formed. Okay, so it's very, very subject to what the C nu B, what exact properties, how much energy density the C nu B has, and how it's affecting the expansion rate. And helium-4 is one of those elements that is particularly sensitive to the precise number of N effective. And what they found when they did that analysis is already back in 1977 is that N effective has to be smaller than 5. Okay? And today, of course, we have much better measurements of the light elements. We have helium-4 measurements. That's the YP that shows up here. D divided by H is the deuterium to hydrogen ratio. And we also have helium-3 and other things. And at the moment, if you analyze this data, the inference shows that the N effective parameter is 2.88 plus or minus 10%. So we can measure this really well. And the number that is being measured here, that has been measured, is the value that has been measured is very, very close to 3. Okay, so we have indirect evidence that there is energy density that is consistent with 3 families of neutrinos, okay, thermal neutrinos. These days, of course, we have more ways to probe the neutrino background, and in fact, people are mostly when they talk about N effective constraint. Yes. Yeah.
The earlier constant that you showed in effective 3 point something.
Yeah.
That was only from CL.
This one?
No, the previous one.
This one? This is a theoretical prediction. That's a theoretical prediction. Yeah. There's some error bars around it because there are input parameters. So for example, we need to take into account things like oscillations. And the oscillation parameters are only measured so well. So we propagated that error, and that gave us these error bars. But that's a theoretical prediction.
Next one is sort of the
That's an experimental result.
but from everything together.
That's from helium-4 and deuterium abundance. Yeah. And I'm moving on to CMB now. Okay. So, well, I said, yes? Yeah. Yeah, mixing doesn't really come into play when it comes to measuring neutrino masses, but I'll get onto that later on. Yeah. Okay, so as said, we can also look for this n-effective parameter in the CMB anisotropies. So you've probably seen these pictures of the CMB anisotropy. So this here is a map that was put together by the ESA Planck CMB mission, which was operating in 2009 to 2013. Their last data release was 2018. And what this map here, the first map here, shows are the temperature fluctuations that are 1 part in 100,000. Okay, so the blue spots are the spots that are a little bit colder, the red spots are the ones that are a little bit hotter. But they are tiny fluctuations of order 10 to the minus 5. Okay? That's not the only kind of fluctuations that you can see. And in fact, Planck and other observations before Planck had also measured the polarization fluctuations. Okay, so we have the if you recall, we talked about photons scattering off electrons, and that process is Thomson scattering, which is polarizing. Okay, so we also expect to see polarization fluctuations in the cosmic microwave background, and indeed they have been measured, and they are very tiny. They are like 1 to 10% of the temperature fluctuations, so really, really highly suppressed. Nonetheless, they have been measured. Now, what you can do with these maps essentially is to, well, I mean, you can look at the map, they look very cute and pretty, but if you really want to do physics with them, what you need to do is to kind of condense the information in the map into summary statistics. And the most common thing to do is to compress this information into endpoint correlation functions. And if these fluctuations are random, totally random, so drawn from a Gaussian distribution, then the 2-point correlation suffices to describe everything about the correlation statistics of the fluctuations. Now, if you go to harmonic space, the 2-point correlation function is equivalent to what is called power spectrum. And what we are seeing here in this plot on the left, that's the power spectrum of fluctuations in the temperature of the CMB. Okay, so you go from this map here, you look at the statistic of the fluctuations, and that's the power spectrum that describes it. Okay? You can also do the same thing with a polarization map that gives you this polarization power spectrum. And you can also take the two maps and cross-correlate the fluctuations, leading to this cross-correlation power spectrum over here. And the thing about these power spectra is that they are very powerful because they are not, well, they're obviously sensitive to what happens on the last scattering surface, but also because the photons have to travel from the last scattering surface to us, and while they're doing this, they pass through a lot of stuff. That means that these CMB photons are also very sensitive to what happens in between the last scattering surface and the present day. And so you can use them to constrain a lot of things. For example, here, you can constrain the spatial curvature, because if you change the spatial curvature, the power spectrum will look different. All the power spectra will change. Okay? Similarly, if you change the fraction of baryonic to non-baryonic matter, so non-baryonic matter is also, well, dark matter if you like, you can also get a huge change in the CMB power spectra. Okay? Similarly here, this is actually a initial condition, a parameter that describes the initial conditions of the universe. So this NS here is called a primordial spectral index, and it basically describes the spectrum of fluctuations that you should expect from inflation, and you can also constrain that. So in fact, it's by looking at the CMB that we have come up with, mainly looking at the CMB that we've come up with these cosmic pies, where we have where they show that we have 75% dark energy today, 26% dark matter, and a little bit of atoms, etc. But there's also another pi that you probably don't see so much, and it's actually the same lambda CDM model, but at a much earlier time. Okay, so this pi here corresponds to the composition of the universe 13.4 billion years ago. So 13.4 billion years ago was basically the time of the last scattering surface. And already you can see here that we have neutrinos at 10% and photons at 15%. And that is because within the lambda CDM model, we just fix this N-effective parameter to 3.044. Okay, if you want to fix this N-effective parameter to 3.044, this 10% versus 15% neutrinos to photons is something that naturally pops out. But there's nothing to stop us to float this parameter to see if the data would actually find this number again. Yeah, if you leave it as a free parameter, will my data find it again? And indeed, it does, actually. So this here is the measurement from the inference of N-effective from the Planck measurement. Okay, it's kept as a free parameter in the analysis, but again, the data find something that is very close to 3. So again, that's a very strong indication that what we think about cosmology and what we know about neutrinos is correct. Okay, just to give you an idea of what we're looking at here. Essentially, the signature of N-effective on the CMB is also on the expansion rate, but now this time we're looking at the expansion rate at the time of photon decoupling or recombination, and the signature actually shows up here in what is called a damping tail, and that is because the expansion rate changes the diffusion rate of the photons in free electron soup. And that changes the way the CMB fluctuations are damped away. Okay, so as you can see, 3 is the blue line, which is totally consistent with data. And if you change N-effective to 2, you get a larger signal. If N-effective is large, like 6, you get a more damping. Okay, so that's what's happening. But again, I stress again, the measurement from Planck, and it is completely consistent with there being 3 families of neutrinos with the properties we expect. Yes? This one here is actually, TT means temperature power spectrum, TE is the cross correlation, EE is the polarization, and then there's also another ton of cosmological observations all together, put together. If you just take the CMB temperature measurements, you wouldn't get a 10% measurement. It may be 20%. But if you put all the available data together, you get a 10% accurate measurement of this number. Okay, so it's definitely not 0, which is already something. Okay, so the take-home message so far is that we have this cosmic neutrino background, which is a fundamental prediction of cosmology, FRW cosmology, that is, well, as fundamental as the prediction of a CMB. We can't really detect it, but there are strong indications indirectly that there is such a background. Okay, so at this point, I'm going to move to the second part of the talk on neutrino hot dark matter. Right. So I hope you're all convinced that there is a cosmic neutrino background. But one thing I haven't considered yet is neutrino mass. And we have we have the discovery of neutrino oscillations back in 1998. And that's a strong indication that that basically means that some neutrinos, at least one neutrino mass eigenstate, will have a mass. Okay. So what this means is that if I use this experimental fact, and then I put it together with a prediction of the C nu B, what I have to conclude is that the background, the C nu B background that we're seeing today, is a massive background. It's not just a radiation background. This has to be so because even though when you make these neutrinos, they are a relativistic particle, universe expands and everything cools, and at some point, these neutrinos would also cool to a very low energy, okay, low temperature. As I already mentioned, the neutrino background we expect to be at 1.95 Kelvin today. If I translate that to natural units, that's about 10 to the minus 4 electron volt. Okay, so if I have a neutrino that is 1 electron volt in mass, then that neutrino will have to be non-relativistic today. Okay, And in fact, you can try to calculate what is the energy density in a non-relativistic neutrino background. And it's usually represented by this very simple expression over here. So omega nu is the reduced energy density parameter in neutrinos. And it's proportional to the neutrino mass divided by some factors. Okay, so it's a non-relativistic background. And what it means is that if you have some non-relativistic stuff that's floating around, then it's sort of like a dark matter. Okay? Now, that's the expression for the reduced energy density in neutrinos. Can we put a number on it? Well, actually, not really. And that's because we don't really know what the neutrino mass is, the absolute neutrino mass scale is. But we do have some ideas about the range that this parameter should take. So the first piece of information we have comes from neutrino oscillations. So as I mentioned earlier, the discovery of neutrino oscillations indicate that neutrinos, at least some neutrinos, are massive. And in fact, at least one neutrino mass eigenstate should have a mass that is larger than about 0.05 electron volt. So if I take this number here and stick it into this expression, what I'll find is that this omega nu has to be larger than 0.1%. Okay? So that's a lower limit on what this omega nu has to be. At the other end, we also have an upper limit. And that comes from tritium beta decay. So you've seen the schematic before in relation to the cosmic neutrino background detection. But these days, when people talk about tritium beta decay, they are really concerned with this endpoint spectrum of the electrons due to this decay process. Because that's a way, by measuring the true endpoint of this spectrum and how far it is away from this Q value, which is the difference of the two nuclei masses, you can, if you can measure this gap, you have a handle on a neutrino mass. And if you look at the number that's been measured by Katrin at the moment, the limit they have on the effective electron neutrino mass is 0.9 electron volt. Okay, so that's the effective electron neutrino mass. There's no equivalent measurement for the effective muon neutrino mass or the effective tau neutrino mass. But we know from oscillations that we have large mixing between the different flavors. So a fairly good guess, if I want to estimate what is the neutrino mass sum, which is what is relevant for cosmology, you can just multiply it by 3, and you get it should be 2.7, not 0.27, sorry, a typo in my slide. And that gives us an upper limit on omega nu of about 6%. Okay, so what this means is that we have a range here, 0.1% to 6% in the form of neutrinos, and they will form a kind of subdominant dark matter component. Okay. Now, the next question is, can we narrow it down any further? Possibly, if we have another better tritium beta decay experiment than Katrin. But as it turns out, the best limit we have at the moment, the best way to limit this range at the moment, that we have at the moment, is actually coming from cosmology itself. And this is how it works. Okay. So cosmological neutrino mass measurement. And let me just tell you that, although people talk about cosmological neutrino mass measurement a lot in the last decade or two, this is actually a really old idea that again went back to the 1970s. So this is 1972, a paper by Kausick and McClellan. And essentially what they did is to take, this omega nu, the expression for omega, expression for omega nu, and then they said, if I demand that omega nu is less than 1, then you can immediately put a bound on the neutrino mass sum. And what they got was essentially a bound on this neutrino mass sum of 24 electron volt, okay, by demanding no overclosure. So that's the simplest kind of neutrino mass bound that you can do. But these days, of course, we are a lot more sophisticated than that. And the way we try to measure neutrino mass from cosmology is by looking at the impact on the C nu B on cosmological observables. In particular, we want to look at the impact of C nu B on how the inhomogeneities of the universe evolve. Okay, so the observable primarily are these galaxy clustering surveys. So basically, what I'm showing you here is a map of the nearby galaxy as mapped by the DESI, it's a dark energy spectroscopic instrument out to a redshift of about 0.2. And this clustering here, like the CMB and isotropies, also contain a lot of information on the energy content of the universe. Okay, so what happens if I so now if I look at a universe that contains only cold dark matter, okay, which is the one that is here on the left hand side, and if I look at a universe that is predominantly neutrino dark, it's actually more or less equal mix neutrino dark matter and cold dark matter, what you see is that they evolve very differently. So they start out the same way, but if I let them evolve, then what I find is that the universe that contains only cold dark matter will have a lot of really, really fine structures, okay? Whereas the universe on the right-hand side is the one that has a mix of cold and neutrino dark matter, pretty large mass. And what you see here is that on large enough scales, it looks more or less the same as the cosmology on the left-hand side. Okay, so you have a large filament over here, which is also visible over there. There's a large empty region over here, which is also more or less visible over there. Okay, so if you squint your eyes, they look similar. But if you look closely, what you see immediately is that the universe on the left has a lot of fine dots. Okay, so think about each dot as a galaxy. You have a lot of small galaxies in this universe over here, and only the large structures like clusters that you see on the right-hand side. Okay, and that is really how we measure neutrino mass from cosmology, which is basically just looking at how neutrinos affect massive neutrinos affect the final distribution of galaxies and galaxy clusters in the universe. Now, as for the CMB, we don't just look at these pretty pictures of simulations and then contrast them with pretty pictures of surveys. What we do, again, is to boil these pictures down to summary statistics. And the summary statistic that we normally use is that of the power spectrum. Okay? So this here is there are two power spectra in the picture. And what we're doing here is to, that's the power. And on the horizontal, what we have is called a wave number. Okay, wave number is the inverse of a length scale. And basically what it means is that if you're looking at structures on large scales, you'll be looking at things on the right, and power in the small scales will be represented by the power spectrum to the right. Okay, larger wave numbers correspond to smaller scales. And there are two power spectra on this plot. And the purple one over here corresponds to the cosmology with only cold dark matter and no massive neutrinos, okay, just only massless neutrinos. And the one that is yellow is a cosmology that has, where we have replaced some of the cold dark matter with neutrino dark matter. Okay, and in this case, it's just one massive neutrino species with a mass of 1.2 electron volt. It's completely unrealistic these days, but just to highlight, just to exaggerate the signal, I've chosen these numbers. And what you can see immediately is that these two power spectra overlap very nicely when you look at the small wave numbers or the large scales. But if you go to the small scales or the large wave numbers, they start to deviate, okay? Where the yellow line here dips below the purple line, okay? And that's basically the summary statistics for those two simulations that I showed you before. And the loss of power that we see here at these large values of K is basically representing the missing fine dots in the simulations, okay? And the cool thing is that the amount of suppression that you expect to see is more or less roughly proportional to the sum of the neutrino masses, and which is why this is a very powerful way to measure neutrino masses, okay? And in fact, the larger the neutrino mass sum, the stronger the suppression that you would expect, okay? That's the leading order signature. There are also some finer signatures depending on exactly how you arrange the neutrino masses. So you could have normal ordering or inverted ordering. There will be some fine differences maybe around here. But this proportionality of the suppression to the neutrino mass sum is the leading order signature. There are many surveys that are able to measure this power spectrum. So the CMB, for example, the CMB primary anisotropies is probably the most powerful when it comes to constraining the large scale part of the power spectrum. But as you move to the smaller scales, other surveys also come into place. So the CMB lensing potential is sensitive to this region, galaxy clustering over here, cosmic shear is another word for weak gravitational lensing, cluster abundance, Lyman alpha, so on and so forth. Okay, so that's my schematic. But there's also, of course, realistic measurements that is represented by this plot. So that's a compilation from the that I took out of one of the Planck papers from 2020, and they're basically showing here all the data points from various types of measurements, like CMB, DES is a cosmic shear survey, SDSS, that's a galaxy clustering survey. So you can see that this power spectrum is all covered, more or less, and we can use this and compare with the predictions of the power spectrum, including neutrino masses, to see which is more consistent. And at the moment, we don't have a measurement of neutrino mass yet from cosmology, but we do have some very tight bounds on the neutrino mass. So depending on exactly how you do the analysis, the bounds normally fall in the range of 0.1 to 0.5 electron volt. These numbers probably don't mean anything to you, but if you compare this with what Katrin is able to do, then at face value, these bounds are a factor of 6 tighter than what Katrin can do. Yeah, Katrin, the equivalent bound would be about 2.7 electron volt. Okay, so that's pretty amazing. But having said that, there's always this mandatory cautionary note that I show at every cosmological neutrino mass talk. So even though I call this range of bounds from cosmology pretty conservative, in the sense that it encompasses most reasonable variations on the limit, depending on how it's extracted. It's not entirely impossible to get away from these bounds if you're creative enough. Okay, so there are people who try to come up with, for example, things like late-time neutrino mass generation mechanisms. Okay, so like in these fits here, we always assume that the neutrino got their mass at a very, very early time in the universe, and so they have, they are massive throughout. Okay, and you just have to wait for them to become non-relativistic for their mass effects to show up. That's the standard picture. But if you're creative enough, you can probably say, well, I have a mechanism that generates a neutrino mass at a very, very low redshift. Then it is possible to bypass these bounds. Okay, so that's one of several studies over here that ask, what might happen if that was the case. There are other ways to get around these bounds as well. So these guys here were proposing maybe the Fermi-Dirac distribution is not the exact distribution. It should be it might be slightly distorted because of some non-standard interactions, whatever. There are even people proposing neutrino decay to get around these constraints. So it's not entirely impossible to get around these bounds if you're creative. But of course, you have to ask yourself how much will you believe in these non-standard scenarios. Okay. But good news is that Katrin, at the moment, the sensitivity at the moment they're bound to this neutrino mass sum as 2.7, but they are expected to get better and better. And finally, the expected sensitivity of Katrin will be about 0.6 electron volt. So it can get down to the cosmological range, okay, eventually. Yes?
What about the cosmological limits? They will also perhaps improve.
They will also improve, which is actually the next slide. Yeah. So the cosmological limits will also improve. So this list here shows several future experiments. Actually, Euclid was already launched last year in July, and their expected sensitivity, 1 sigma sensitivity to the neutrino mass sum is 0.01, okay? Which means that if the neutrino mass is exactly 0, then the 95% confidence limit would be between 0.022 and 0.04, okay? LSST, which is probably going to happen sometime, who knows, will also have something that's similar. And of course, in the far future, well, not that far, okay, beyond 2030 maybe, CMB-S4 would also be sensitive to this mass sum as well, okay? So in other words, if you look at these numbers, if the true neutrino mass was 0.06 electron volt, okay, which is the minimum that we'd expect from neutrino oscillation experiments, then with these sensitivities, a 3 to 5 sigma significant detection will be possible in the next 10 years. So that's what we're looking at. So I said Euclid was launched in July 2023. It's a dedicated weak lensing survey looking at percent level distortions of distant galaxy images due to photon diffraction. So you have a galaxy image, and then the photons come to us, and it's lensed by all the large scale structure that is lying between the galaxy and and the observer, that's us. And if you look at these distortions and the statistics of these distortions, then you can also get an idea about the statistics of the intervening large-scale structure. So that's what they're doing. This ESA Euclid. There's a small variant, and that's the weak gravitational lensing of the CMB, which is idea is similar. You look at the CMB map, and then you look at small distortions of this map, which is also a way to probe the large-scale structure. This is actually already being done by Planck, and this is the what is called the lensing potential power spectrum, basically just extracting this lensing signal. And coming up is CMB-S4, as said. They are also a lensing experiment, CMB lensing experiment, but it's slightly different because they're looking at polarization. Okay, so the CMB-S4 experiment is basically 12. The idea is that you put 12 telescopes at the South Pole and in the Atacama Desert in Chile. And the idea here is that instead of measuring the full sky, as Planck and WMAP did, it will be looking at fluctuations of the CMB on very small scales, so like on scales of less than 1 degree. And what they want to do is to reconstruct that lensing potential from the lensing signal. Okay, it's a joint DOE and NSF effort planned for the 30s. And if you've been following SNOMAS and all that, you would probably know that this is like the high priority experiment as recommended by P5. Okay. So do I still have a couple of minutes? Yeah? Yeah, okay. It's just short anyway. So that was neutrino mass, and also mentioned N effective. But these are not the only parameters that we can measure. These are just the standard parameters that we can measure, okay? Because it sounds like a good idea to measure these things. There are other things that we can probe with cosmological observations as well about neutrino physics. So some of the things we can do is to look for neutrino decay, for example, and that's essentially exploiting the fact that the universe is 13.8 billion years old. And if the neutrino has an extremely long lifetime, you probably won't be able to see neutrino decay in an experiment. But if you have the whole universe, which is 13.8 billion years old, to test a decay, you can put a bound on a neutrino lifetime. Similarly, we can also look at try to find neutrino self-interaction effects in these cosmological observables. And again, what you're exploiting here is the fact that in the early universe, you have this dense soup of stuff. So interactions can happen more frequently and more efficiently than you would find than you would ever be able to achieve in a laboratory. I mean, in the early universe, you have a soup of neutrinos. You can't create a soup of neutrinos in your lab. Okay, so that's what we're exploiting. And just very quickly, as I said, you can look for neutrino decay and therefore measure a neutrino lifetime. And in fact, CMB bounds on a neutrino lifetime are extremely competitive. So over here, what I'll show you here is, it's hard to see, but this blue line here is essentially it's the lower limit on a neutrino lifetime. So everything above is allowed and everything below is excluded. And it is at the moment the tightest bound that we can get, the best bound that we can get on the neutrino lifetime from any kind of measurement. Just below that is the limit that we get from IceCube. And okay, in that kind of experiment, you're exploiting the fact that extragalactic neutrinos are traveling a long distance, and so you can see if they have decayed. But if you look at other ways to try to pin down a neutrino neutrino lifetime, like from BBN or solar neutrinos or laboratory neutrinos, these bounds are not even competitive to show up on this plot. So CMB limits are really the best at the moment we have on a non-radiative neutrino decay process like that. Okay. As said, the other thing we can probe is neutrino self-interaction, and in fact, there's a backstory to neutrino self-interaction. People were trying to explain away the Hubble tension by making neutrinos self-interact, and the claim here is that if the neutrinos have an additional interaction that is given by this, that has an interaction strength given by G effective that is 1 billion times larger than the Fermi constant, then it's possible to have, reconcile the Hubble parameter measured by the Planck mission and that measured by the local observations like Holy Cow or Schulz. Okay, I'm not saying I'm endorsing the solution, but people have done it and it's getting quite a bit of attention. all around. So that's all I have to say today. I think that's exactly an hour. And I leave you here with my summary, and thank you for your attention.
Thanks, Yvonne, for the excellent talk.
So for the cosmological structure formation simulation, what neutrino physics actually goes into it apart from the mass and then its nature like relativistic? The
So-
question I have is whether any other warm or hot dark matter model will equally suppress the power spectrum, or do you have any extra feature on the power spectrum which is coming from neutrino?
Yeah, so that's a very good question. The only thing that cosmological observations are sensitive to is kinematics. That's it. So they could be neutrinos, they could be any other hot dark matter, as you said, axions, whatever, they will also produce a similar kind of suppression. But the thing is that if you have another kind of hot dark matter, you have to worry about what they were doing at early times. So let's say axions, okay, QCD axions. A QCD axion that is maybe about 0.5 electron volt would also give you this kind of suppression. But the thing is that at the same time, they would also contribute to this n-effective parameter. So if I have an axion, I will increase the n-effective from 3 to maybe 3.5 or 3.0, 3.1 or whatever. So I have two handles on constraining those scenarios. Yeah, I can look at the n-effective contribution, and I can look at the suppression as well. So that's, I mean, cosmological observables are not sensitive to quantum numbers. Okay, so it's just something that's hot, has certain kinematic properties, and that's it, essentially. Yeah.
So even with that, even in the extreme case, the contribution of omega neutrino remains subdominant for the dark matter.
Yeah.
So the rest has to be cold dark matter.
Yes.
With some beyond standard model.
Yeah, that's right. Yes, could be warm, because the warm dark matter signature is at a much smaller scale. So you could have a warm dark matter and neutrino dark matter, and the same constraints would still apply. Yeah, warm dark matter, you would also expect some kind of cutoff in the power spectrum, but the scale at which that cutoff occurs would be at the dwarf galaxy scale. Okay, so it's a much larger value in K, and so not the region where we extract the neutrino mass bounds. Yeah.
Is there a physical reason to understand why makes you suppress the power spectrum?
Okay, so structure formation with cold dark matter basically relies on a very fine balance between the kind of matter that drives expansion and clustering matter. Now, if I have non-relativistic neutrinos, then they will contribute to the expansion in the same way as the cold dark matter. But if you look at the small scale clustering, they are different, okay, because they don't like to cluster. So basically, the suppression comes from the fact that you have a mismatch between these two things. So on large scales, they are exactly well matched, so it's all good. But on small scales, there's a mismatch. Okay, so yeah. So if you every time I replace cold dark matter with neutrino dark matter, the larger, the more I replace, the larger the mismatch, and so you have this suppression. Yeah.
So can you tell something about the hierarchy measurement in cosmology?
Hierarchy measurement. So hierarchy measurement, I'm not sure if I have anything like that. So the yeah, I don't think I have a slide on that. But
Some of the masses we can.
yeah, so the only handle we really have now, and in the near future on measuring the hierarchy, is to look at what neutrino mass sum we measure. Okay, we cannot really resolve the individual masses, and in fact, I can, even if with Euclid data, I will not be able to do that. So I can try to do I mean, I've done this exercise at some point. You can generate some fake data and then fit it with mass hierarchy, normal mass hierarchy. You fit it again with an inverted mass hierarchy. The difference in the preference in your chi-square is maybe 1. Okay, so you can't. The data will not be good enough to tell. You really need to have, if you want to be able to resolve the individual neutrino masses, you need to have a neutrino mass sum measurement that is maybe 20 sigma significance. And then we can start talking about the individual mass, measuring the individual masses.
No, I cover the mass hierarchy, the normal versus
Yeah, I mean, okay, you can only rely on the mass sum to do that. So if you have a measurement that is 0.05 electron volt, then obviously that is not inverted mass ordering. But that's the only handle we have. We can't actually resolve. We will not be able to resolve the individual masses in the near future.
Below 0.05.
If we have below 0.05 electron volt, I don't know what we're talking about anymore. We probably have to revise the cosmology. But if you get a measurement that's between 0.05 and 0.11 electron volt, then you're probably in the normal hierarchy. Okay. Yeah, so that's the only handle we have. We can't say anything about the mass spectrum. Won't be able to. Yeah, not in the near future.
Are there other questions?
Yeah.
Direct detection of the neutrino background, there is no hope for this.
Pretty much no hope. Yeah, so actually Andre mentioned this earlier today. So people have thought about another idea of, so the main problem with something like Katrin is that the tritium source is gaseous. So you have a limitation on the resolution because this tritium gas is flying around so fast. So what people thought about is to use graphene and then embed the tritium atoms in on the lattice sites, which sounded like a good idea. But in the end, if you look at the quantum mechanics of it, the uncertainty principle tells you that you still won't be able to achieve the resolution required to do this detection, because the tritium atoms are not just sitting there not doing anything. Okay, there's a bit of 0-point energy. So yeah, so that's the best idea at the moment, but no, probably won't work anyway. Yeah. Yeah. What is it about tritium that is most suitable? Actually, I'm not quite sure. I'm not quite sure why it is that they always use tritium. I never. Is it just the energy? It's just the endpoint energy is easy? Yeah? Okay.
There's also polonium.
Yeah. I mean, I've seen people calculating the rates, and yeah, but yeah, I guess it's just maybe that it's easier to resolve. Yeah.
Also, so you said that actually what you want to see will just be monochromatic.
Yeah, more or less. There's some spread.
Yeah, but I think morning we were discussing that actually by now since it has decoupled into 3 mass items.
You should have 3. Yeah, you're right. Yeah. You should have. Yeah, I think so. Yeah, you should have 3. You should have 1 main peak and then some small ones as well. Yeah, of course. Yes. Yeah, in principle, yes. In principle, yes. If you can resolve it, yes. Yeah. But of course, as said, it's just hard to do. It's not even easy to measure neutrino mass. And the thing is that my schematic doesn't do it justice. That endpoint spectrum is huge compared with this tiny signal at the end. It swarms everything out. Yeah, swarms everything out because of the the end. Yeah. So.
Are there other questions? Okay, not.
Oh, there's one over there.
This maybe this doesn't have anything to do with unity, but I think in the relic slides, you showed that when the decoupling happens, so electrons and positons are both. So are you sure that leptogenesis happened after this decoupling?
Before, that's the expectation. You mean the neutrino decoupling you're talking about? Are we sure that? Okay. As far as I know, all the theories for leptogenesis or baryogenesis happen at much higher energies. Much higher energies. So we're talking about maybe. I mean, if I look at standard leptogenesis, that heavy Majorana neutrino mass is 10 to the 12 GeV or something like that. Yeah. So extremely high energies, not 1 MeV. I don't know if there's a leptogenesis mechanism. I mean, you can probably. Yeah, I'm not sure if there's a baryogenesis mechanism that operates at such a low energy. I'm not sure you can do it. And anyway, we know that there are baryons, and there are light elements. So at the time of nucleosynthesis, you should already have generated that anti-matter asymmetry. Yeah. So, which is basically a few seconds to 20 minutes. The asymmetry should already be there, existing.
Okay, are there other questions?
Okay.